Hello again, quantum friends. We pick up our journey through the quantum world by focusing today on the two-slit experiment. You've already taken a look at a simulation of acoustic interference, and you've, for your own ears, listened to the interference between two speakers on your laptop, for example. And you'll remember what the simulation looked like. Again, we have two sources. This is rotated 90 degrees from how it appears on your screen, as you can see by the words over here. But we have these two sources, the speakers, emitting acoustic waves in a way that the sound from one, or the waves from one source, interfere with the waves from the other source, and you get this interference pattern of loud and quiet sounds throughout the room. And as you walked around the room and you covered one ear, you could pick out those regions of loud sounds and regions of quiet sounds. And hopefully you also played the game of standing in a silent region, turning off one speaker, and the sound in that region would increase. So you can see that more speakers on does not equal louder sound necessarily, because waves can combine in a way that's destructive to cancel out sound, or constructive to enhance sound. As a preview about what we expect to see in the world of quantum, we're going to find that quantum particles have the ability to behave like waves. And whether it's a photon or an electron or an atom, those particles, which we'll call quantons, can interfere in much the same way that sound waves can interfere. So we're going to build this intuition about how waves behave and use that when we are talking about particles in the quantum world. Now, when we talk about waves, we're not restricted to thinking about sound waves. We can talk about anything that is wave-like. And so you've seen other examples of this as well. For example, in the Veritasium video that I asked you to watch, we see that a disturbance of the water in two different locations sends out these circular wave fronts that interfere in a way that can suppress or enhance the wave size on the water. You can actually see this also with ducks swimming. Sometimes you'll see one duck swimming next to another duck, and they will be kind of shedding off their back. They'll be shedding these circular wave fronts, and those wave fronts will interfere, and you'll get this pattern as well. And of course, we saw that our very good dog could also emit waves. And the wave fronts from the various parts of this little doggo's body interfere constructively and destructively, creating this interference pattern as well. As you can see here, when we zoom in a little bit, you can clearly see these wave fronts emerging from the body of the dog. And as a reminder, this is happening right on our campus, right? This is Lake Waban about 1.5 years or 2 years ago. So interference is all around us, but in our daily lives, we tend to think of interference as applicable to waves, light waves, sound waves, water waves, etc., but not to particles. So in our language that's built in the classical world, we have this distinction or a boundary between particle-like and wave-like. So let's see what would happen if we use particles instead of waves. So here we have a device that has two slits cut out of it, and we just drop a pile of sand onto that cardboard with the slits. And what we see is that some sand makes it through and some sand is blocked. And not surprisingly, we think of this sand as particles. And so we basically get a pile of particles below one slit and a pile of particles below the other slit. But there's certainly no interference pattern to speak of, right? We just have two piles of sand. We can draw this result schematically. So I have the same diagram shown on the previous slide I show here. I just rotated it 90 degrees to match my sketch. And so we have a source, so this is a bucket of sand, pouring sand onto two slits or two holes. And if you only have one slit open, you would get a pile beneath one of the slits. If you only had the other slit open, you would get a pile beneath that slit. With both slit 1 and slit 2 open, you get the sum of the distribution of a single slit. Okay, so you have a two-humped pile of sand. Okay, no interference, no bright and dark spots or high and low spots, other than a high spot right below one slit and a high spot right below the other slit. So the sand is not interfering. We just add up one pile with the other, and we call that particle-like behavior. What we are going to find, though, is in the quantum world, there is no real distinction between particles and waves. All objects, all quantum objects, have wave-like behavior and have particle-like behavior. So we'll see that things that we have thought of perhaps as particles actually will demonstrate interference or exhibit interference in a two-slit experiment and in other contexts. And that's actually a main takeaway that I want you to carry with you after this course is done. That when you see interference effects, that's indicative of wave-like behavior, even though the objects that exhibit that behavior are not necessarily what we think of in the classical world as waves. I've also asked you to watch a video showing the two-slit diffraction result for sunlight, which is composed of light of all different colors or wavelengths, red, orange, yellow, green, blue, indigo, violet, so to speak, for the colors of the rainbow. And what you found in that video was that sunlight shining onto two slits produces this interference pattern, but we have this separation in color as you move outward from the middle of that pattern. Notice the first peak is white, but then subsequent peaks, you see this color separation. And actually, as you go to later and later peaks, you get more and more separation, right? So if you take a look down here, you have a white blob in the middle, then you have red, white, yellow, red, blue, white, yellowish, red, but then now you're starting to see some green. And then if you come down here, this collection, you have like a blue and a green and a red, and they're fully separated. There's no overlap. So there's no whiteness in that blob, which would indicate the overlap of all of the colors. So I thought it'd be helpful to spend just a few minutes talking about why this happened. And the main reason here is to give us a sense for why we get this pattern to begin with. In other words, what is the physics behind the two-slit experiment and this so-called diffraction pattern? And why does the spacing between peaks depend on the wavelength or color of the light that you're using? So here I'm showing you a snapshot of a simulation/animation taken from this great website called ophysics.com. This particular animation is at ophysics.com/l4.html. It's not, ophysics.com is not strictly about optics. It's general simulations in physics, but they have a lot having to do with light, waves, and optics. And it's a really beautiful site, easy to use, and I recommend it. It's fun to explore. What we have here is a two-slit experiment shown a little bit schematically. So these locations represent the source of the slits, basically, so where the light is emerging from. Here, one wave is green and one wave is red. That does not indicate like green light and red light. They're just trying to mark one signal from the other, so that when things get combined down here, you can distinguish one from the other. So these both signals have the same wavelength in this experiment, and you can adjust the wavelength here. Now notice that we are looking on a screen far away at a point that's midway on the midline between the two sources. And we're asking, are we going to get constructive or destructive interference here? In other words, when a peak of the red wave arrives, does a peak from the green wave arrive? Are they in phase? Meaning, are they arriving in sync with each other, or are they out of sync with each other? Okay. Well, the way that you can tell if they're going to be in sync with each other or not is if the distance between the source and the target is the same, and if the sources start out in phase, meaning when a peak is emerging from the first source, a peak is also emerging from the second source, and when a valley emerges from the first, a valley emerges from the second. If that's true, and if the distances that the light has to travel is the same from both slits, then they're going to remain in phase. They're going to remain in sync, and you'll get constructive interference. So this would be a bright spot. Okay, so we expect a bright spot here. Okay. Now notice I'm doing this for a particular wavelength. They don't say anything about the units, but the wavelength here is 4.8. Okay, and we're going to explore two different wavelengths. We'll call this the short wavelength, and then we'll have a long one, which is twice as long. Okay. But if we're on this line, this midline between the two slits, we're going to get constructive interference. Okay, so this is constructive interference. And that's a synonym for a bright spot. Let's see what happens if I double the wavelength. Okay, so I'm going to increase the wavelength. Do I still have a bright spot at this location? Let's take a look. So here I've increased the wavelength. Okay, I haven't quite doubled it, but it's almost a factor of 2 larger than it used to be. And the question is, do I still have my waves arriving in phase, in sync, at this point here? And the answer is yes. Look, at this point right here, the red wave is basically near a peak, and the green wave is near its peak. So we have peak arriving with peak. So we're going to get a bright spot here. So once again, we have constructive interference. And indeed, this is a general result, that no matter what the wavelength is, no matter what wavelength we use for light, no matter what color light we use, on this axis, midway between the two sources, the distance that each light ray has to travel is exactly the same. So if the two light rays start out in sync or in phase, they will arrive in sync or in phase. In other words, you can fit the same number of wavelengths of light in each path, and therefore these two waves will arrive in sync. Just so we're clear, when I say wavelength of light, what I'm talking about is the distance between one peak of a wave and the next. And we'll call that the wavelength. And we'll use the symbol lambda for that. That's the Greek lowercase lambda, which is often used as a symbol for wavelength. So then the statement is, if we have the same number of wavelengths in each of these two paths, then a signal that starts out in sync will arrive in sync and will have constructive interference, meaning a bright spot. And what we saw is no matter what the wavelength is, this is going to be satisfied because for this point on the screen, midway between the slits, the two paths are exactly the same. And this is exactly why in the two-slit experiment with white light, we see that on the axis in the middle of the device, we get constructive interference for red light, for blue light, for green light, and so on. And so what we get then is the addition of all of those colors. And when you add up all of those colors, you get white. So we see a white spot in the middle of our diffraction pattern. But let's see what happens when we go off axis, when we go further up on the screen. We're not going to continue to get white spots. We're going to get a separation of color. So let's take a look at the reason for that a little more closely. So here, this is the same simulation from the same website, except instead of looking on the axis between the two slits, I've increased the height, this y parameter, to move away from that axis, okay? Now, I'm still using one of the wavelengths I used before, 4.8. So this is my short wavelength of the two, okay? And what I see is, as always, in all of these simulations, the light is coming out of the source in sync, okay? So it starts here with a valley or a trough, and look, it arrives also in sync, which means a valley and a valley will arrive for red and green, a peak and a peak will arrive for red and green, and so on. And that means we're going to get constructive interference once again here. Constructive interference, which is a bright spot at this particular location on the screen. Okay, and here's a really straightforward way to think about it, right? These two path lengths for the red and the green signals, they are not the same length, right? The red has to go further than the green. And that's indicated here with this dotted line, okay? This dotted line, from this dotted line to the screen, those distances are the same. So this is like an isosceles triangle, meaning that two sides have the same length. Okay. And so this length and this length are the same in that triangle. So the extra path for the red is just this part down here. Okay, so the green path is the red path is longer than the green path by this amount. But that amount, notice, is exactly one wavelength. The path difference is equal to one wavelength. And so what that means is, although the path lengths are different, if the signals start out in sync and the excess path length is exactly one wavelength, then they will continue to be in sync. So you can actually ignore this whole part of the red path, assuming that it's an integer number of wavelengths, 1 or 2 or 3 or 4 wavelengths. And you can imagine the sources just starting here and here, in which case the red line doesn't change if you shift it by a full wavelength, okay? But look what happens to the intensity of the light at this spot if we keep the spot in the same place, but we increase the wavelength. So now I'm going to go to the longer wavelength source. And here we have it. The same situation, only we've changed the wavelength to be longer. Now look, we have the green path, which is shorter than the red path by this much, but the amount, you can no longer fit a whole wavelength into this region. You can only fit half a wavelength. If you can only fit half a wavelength, that means these two signals at the location of this dotted line, they're out of sync now. Here we have a signal that's rising to a peak, and in red we have a signal that's falling to a valley, okay? And the consequence is that when these two signals, the red and the green, reach the screen, the red is going to arrive as a peak or close to it, and the green is going to arrive as a valley or close to it. So the peak of the red will cancel the green valley, and we'll get destructive interference, which will give us a dark spot at that location. And so we can see that for longer wavelength light, we're going to have to go further away from this midline. We have to travel further away from the midline before the extra path length here is equal to 1 wavelength. So we're going to have a bright peak, a bright intensity on this midline, and it will taper down to dark around here, and then it will rise up in intensity to a bright spot somewhere up here. So the main consequence is that for longer wavelength light, like red light as compared to blue light, you're going to have to go further from your midline before you get the next bright spot. So blue light will have a peak, a bright spot on the middle axis, on the midline here, and then it will have another bright spot pretty close to the midline, but you're going to have to go further from the midline before you get a bright spot for red light, because the wavelength of red light is longer than the wavelength of blue light. And we can see this effect really, really beautifully here. This is an image I've taken off of a Stack Exchange website about physics and the two-slit experiment. So what we see here is the interference pattern for white light, showing all colors constructively interfering on the axis. And then as you move further off axis, you can see you have to go further before you get the red peak. You have to go to here and in here and in here and in here, but you get a blue peak closer to the axis. And so you start to get these colors separating out. Okay, well that was a little bit of a foray into the physics of light and interference. For now though, let's just focus on a single wavelength. In this case, let's look at red light. And we can ask the question, just make sure that we understand the language to describe interference for a single wavelength of light. And we'll work with this one wavelength to identify and highlight some key aspects of interference. Okay. So the first is that we have these bright and dim spots in our interference pattern, but we can show those graphically as a plot of intensity of light as a function of position. Okay, so wherever there's a peak in our kind of photograph image, we're going to have a peak in our intensity plot. And wherever there's a dark spot in our photograph image, we're going to have a dark spot or low spot in our intensity plot. And overall, there's kind of an envelope of intensity that decreases as you move away from the middle of region of this apparatus. Okay, so we call this multiple peaked structure. We call that the interference pattern. Saying the same thing in a slightly different way, I've just kind of expanded and redrawn the situation here. We have our bright and dark spots in the photograph image, and then we're representing the light intensity as a function of position. And there's an envelope, if you'd like, that describes the overall change in intensity of those peaks as you move further away from the axis. So I'd like to take a moment to just really explicitly call out one of the beautiful features of interference and of wave-like behavior, because we're going to see this all the time in our work with quantum particles. Okay, so up top here, I'm showing the two slit interference pattern and a schematic of the apparatus that gives you this pattern. And we see, we have the bright spot, dark spot, bright spot, dark spot that's characteristic of interference. If you then came in and blocked one of the slits, let's say we block slit 2, that interference pattern is going to go away because there's no sense in which all of these ripples that used to be there coming out of slit 2 are no longer there. They're all blocked. So you're just going to get light coming out of one slit, and you lose the bright, dark, bright, dark, bright, dark patterning. Okay, but let's look at the consequence here. Some of the regions that used to be dark are now brighter. So somehow blocking a hole, which leads to less transmission of light overall, actually enhances the signal in certain regions. So we can say that blocking a slit can enhance or lead to more transmission in some places. And just to be really explicit here, I've identified a vertical line connecting a dim spot in the first diagram, showing that that is a brighter spot down below in the second picture. Okay. Now, you may have seen this also when you did or experienced it acoustically when you did the sound wave simulation on your laptop. You heard if you put your head or your ear in a location where the volume was very low, and then you disabled one of the speakers, then you will have felt an increase or experienced an increase in volume at that location. So turning off one speaker can actually make the signal louder. Just like here, turning off one of the light sources can enhance the brightness of the signal at a certain location. Okay, so let's pause here for a moment and just summarize some of the main results that we have, okay? We've seen that all waves, be it water waves, air waves, light waves, exhibit interference with this two-slit experiment. We've seen it, you've listened to it, we've seen it with a water wave demo on Veritasium's video, and we've seen it with the light wave demos also on Veritasium video and elsewhere. Okay, and our interpretation of this is that the light or the water or the air, the wave emerging from one slit is interacting with the wave emerging from another slit to give either constructive or destructive interference. And we understand that constructive and destructive interference arises because of the path length difference from one slit and the other, as compared with the wavelength of the signal, of the wave, okay? And so I think what we can say as a summary statement is, if you see an interference pattern, that's a hallmark signature of wave-like phenomenon, okay, number one. And number two, a hallmark signature of interference is that if you block a transmission path or reduce the number of ways to go from input to output, you can actually enhance the signal in a certain location. And I really want you to hold on to that idea because we're going to make use of it a lot going forward. So if we were in the 1800s, the story would kind of end there, right? Young's two-slit experiment was done in 1801, and so this idea of interference was known for a very long time. But now in the modern era, we have a much more rich puzzle at our feet that we have to contend with, and that is the following. It's shown here. If instead of shining bright light at both slits, if you reduce the intensity of your source so that you are only sending one photon at a time through your apparatus, it turns out that you can still build up this interference pattern. So that's what's shown here. This is actual data taken, and if you'd like, you can watch at this YouTube video, you can watch as time evolves, you can watch this pattern develop. But this is a detection screen showing light one photon at a time. Each dot here is one photon making it through the two-slit experiment. And over time, each photon is arriving, and we get this pattern building up one photon at a time until in the final picture here, we have this clear interference pattern that we know and love that we saw with a bright light source. But this is a absolutely fascinating puzzle. How is it that you can get this pattern building up over time, even though you're only sending one photon at a time into your experiment, right? If we think about interference as arising by constructive and destructive interference, but you only have one photon. What is that one photon interfering with? In other words, how can you get constructive interference with a single photon? Or how can you get destructive interference if there's only one photon at a time? We will see, and we're going to spend a fair amount of time in the remainder of our term here talking about the details of why and quantifying this. But we will see that it is, we are kind of beholden to our classical language and experience when we think about this experiment. So we kind of envision a photon as being like a massless marble. So it's a point-like object that has a definite position, and it either goes through one slit or the other, or maybe it goes through both. But what we're going to learn is that photons and all quantum particles are not just smaller version of regular particles from our daily existence, okay? They do not have defined or definite positions. Their position is undefined, does not exist until measured. And so we can't really, it's not sensible to think about a particle as starting at point A and moving smoothly from point A to point B through one slit or through another slit. It just doesn't work that way. And as unsettling as it is, that is something that we're just going to have to work with. Okay, so a large part of learning quantum is learning to get rid of your preconceived notions and your kind of common sense understanding of the world. In relativity, we had to give up the idea of absolute time, and we had to give up the idea that an object's length is the same in all reference frames, because we learned about time dilation and length contraction and rear clock set ahead. Here, we're going to have to give up our notion that particles or objects have a defined position and that they travel from point A to point B along defined trajectories. They simply do not do that. And we will present a lot of evidence that supports this rather outlandish but experimentally verified claim. And just to pile it on a little more, if you thought that single photon interference was the only bizarre aspect of quantum, here's another experimental reality that we have to contend with. If you repeat the two-slit experiment, but instead of using photons, you shine electrons, and in the laboratory you can very easily make a source of electrons, a gun of electrons if you'd like, that just shoots a beam of electrons out. You can repeat this experiment, and lo and behold, you get exactly the same outcome. You get this banding structure that's characteristic of interference. And so what we see experimentally is that electrons interfere in the same way that photons do. So then the question is, what does this tell us about electrons? Well, for me, one of the main takeaways here is that we can clearly see that electrons interfere with, they interfere. And so we can say that they definitely have wave-like properties, okay? And if they have wave-like properties, that means they are not just smaller versions of sand particles, right? Sand particles, we know, go through one slit or the other, and they form piles behind each slit, and the total number of particles that makes it through when two slits are open is just the sum of those two piles. Here, we get a different result. We don't just get two piles of electrons, we get an interference pattern. And so here we're seeing that electrons are behaving in a similar way to photons, to light. Okay, so there's some unifying characteristic that joins electrons and photons. So this result then, that electrons behave like waves and interfere, if that's true, then an electron should have a wavelength because it's wave-like, so we should be able to quantify its wavelength. And interestingly enough, this was an idea that was proposed before the experimental evidence actually existed. So there was a PhD student in physics in France named Louis de Broglie, and he, as part of his dissertation, made the proposal that particles could exhibit wave-like behavior too. And this was following on the heels of Einstein's discovery that photons had particle-like behavior, meaning that in that case they were discovered to kick out electrons from matter. One photon would kick out one electron, and so on. And so it was known at the time that photons had wave-like behavior through the Young two-slit experiment, but it was also known that photons had particle-like behavior. So de Broglie kind of filled in the missing piece, saying, okay, well, we know electrons have particle-like behavior, but perhaps electrons and other particles also have wave-like behavior. So he proposed this idea and also specifically proposed what the wavelength of a particle would be. And he stated it was the ratio of a constant called Planck's constant, h, which is a very small number, divided by the momentum of that particle. And the momentum of a particle is given by its mass times its velocity. So, if we look at in the SI units of like kilograms, meters, and seconds, the numerator is 10 to the minus 34. And we are then going to divide that by the momentum. So if we're talking about, say, the momentum of a person who's walking, okay, then the momentum is going to be their mass times their velocity, or times their speed, if you like. And the mass of a person, I don't know, is 50 kilograms, something like that. Call it 100 pounds or so. And their velocity typically is on the order of a meter per second. This is all just rough numbers. So we're going to get a number that's 50 in SI units, in the same units for h being 10 to the minus 34. So when we make that division, 10 to the minus 34, so lambda for a person, it's 10 to the minus 34 over 50, and that would be in units of meters. So we're talking about unbelievably short distances. Okay, so we'll call that, I don't know, something like 10 to the minus 35 or less meters. So that's just ridiculously small. Okay, so part of the reason that you don't see quantum interference on your daily lives is that we're dealing with particles whose momentum is absolutely way too big compared to h in order to have a wavelength that's a reasonable size in meters. Okay, so the scale is just so far off. However, if you look at small or particles with very small mass, like an electron, for example, and if you get them moving at low speeds, then you can get this momentum to be small enough so that this ratio gives you a wavelength in meters that can be kind of comparable to the separation between these two slits. Okay, and so that's why you have to go to the quantum scale or the atomic or subatomic scale to see these effects. And there's a little bit of a caveat to that, because I'll show you in just a minute that it's not just single particles that show quantum interference. So we'll come back to that in a bit. But just a little side story about de Broglie and his prediction. So he was defending his PhD, and his committee did not know what to do with his prediction that particles had a wavelength associated with them, because there was no such evidence experimentally that this was true, right? So his thesis, his PhD, predated any of this experimental work. So his committee was confused, didn't know whether de Broglie was kind of crazy or was onto something. So they passed along his PhD dissertation document to Einstein. And Einstein was really tickled by it and thought, wow, this is a step in the right direction. This guy de Broglie is really onto something, and this might be a moment of clarity at a time where the physics world was trying to sort out all of the mysteries of quantum mechanics. And so based on Einstein's recommendation, de Broglie's thesis committee decided to pass him. And so not only that, but a few years later, two Americans, Davison and Germer, made this experiment and detected, in fact, matter wave interference using electrons. Incidentally, Davison and Germer carried out their experiment in 1927 and earned the Nobel Prize in Physics 10 years later for this experimental result. And de Broglie made his PhD defense in 1924, where he proposed this that particles had wave-like behavior and had a defined wavelength, and he earned the Nobel Prize in 1929. So this idea of particles behaving like waves was really foundational to quantum mechanics and really important in the world of physics in the 1920s, right in the mix of the development of quantum theory. So I said before that fundamental particles like electrons have wave-like nature, but it's not just electrons. So as time has gone on, like here in 1999, there have been results showing larger and larger objects exhibiting interference in two-slit-like experiments. Okay, so here we have Buckminster fullerene or buckyballs, which consist of 60 carbon atoms. Each carbon atom is 12 atomic units, so 12 times 60 is 720. So this object has a mass of 728 atomic mass units, and there was wave-particle duality observed experimentally with these devices, or with these particles. And even more than that, in 2013, a group demonstrated two-slit interference and wave-like behavior for molecules that are 10,000 AMU in size, just absolutely gigantic molecules. But the game didn't stop there. In 2019, there was an experiment done, a two-slit experiment done with a molecule made up of 25,000 AMU, or a molecule that consisted of 2,000 atoms, which is the heaviest object known to date to demonstrate quantum interference with a two-slit-like experiment. So this is absolutely amazing, right? So the quantum interference in that phenomenon, yes, it applies at the subatomic level, but it really is a property of nature. And so if you build up some material out of elements using building blocks that behave according to quantum mechanics, then the thing that you have built will also behave according to quantum mechanics. So let me just summarize what we've seen so far. We know that interference, like a two-slit experiment interference pattern, has been seen for bright light, check, single photons, check, and a beam of electrons. And you might be wondering, if you've been keeping score, is single electron interference also a thing? Okay, and it turns out that yes, it is. And let's see some experimental evidence of that as well. So here we have the result from an experiment with single electrons shot through an apparatus. And after 28 electrons make it through, this is what the pattern looks like. After 1,000 make it through, there's clearly this interference structure. And after 10,000, you have this beautiful banding. So, I mean, this result is phenomenal, beautiful, and amazing. But given the other things we've seen, it just kind of seems like a natural extension, right? Light and particles both exhibit interference. So if single photon interference is a thing, why wouldn't single electron interference be a thing? And indeed, it is. And what we then know is single molecule interference using gigantic molecules made up of 2,000 atoms should also exhibit single molecule interference. So it seems to be a quantum reality that light and particles can interfere even if sent one at a time through this two-slit experiment. So let's take a step back and see where things stand here. We have photons that can behave like particles or waves. We have electrons and other particles that can behave like particles or waves. And so there seems to be this kind of duality in the universe. That nature is sometimes wave-like and sometimes particle-like. But I always found this to be really frustrating. I used to find it disturbing that light could behave like a particle and matter could behave like a wave. But I did realize then that the root of my discomfort was really that this experimental result coming from the quantum level, from the very small scale, was just in conflict with the kind of mental model that I had that described what a particle is, right? For me, a particle was a small marble-like object that had a definite position and was rigid. But why should I expect nature to behave in a way that's consistent with my daily experience, right? Why should it be that an electron is just like a really small marble? It's just not like a small marble. I'm basically 10 orders of magnitude taller than an atom, 15 orders of magnitude taller than a nucleus of an atom. So why would I expect that nature behaves the same way down there as it does up here? So it's been a bit of a process for me to come to terms with this, but I actually find it really comforting and almost natural that light and matter both exhibit particle and wave-like behavior. And rather than talking about this as wave-particle duality, I actually now prefer to use just a different term and call light and electrons and things like that quantons. And I like this term quantons because it definitely makes it clear that we're talking about quantum particles, And so many particles in the language of particle physics and physics end in ONS, like a proton, electron, neutron, and so on. And so I just like the idea that a photon, even, that we can kind of have a generic class of things. I don't even want to say particles, a generic class of things that behave according to quantum mechanics. And so I like this term quanton for that reason. I did not invent this term. I read it somewhere and have latched onto it, and I really don't want to let it go. I have heard other terms that, make me shiver. One of them is wavicle, particle, wave, particle. But I am not a big fan of that one. So I'm going to stick with quantons. If you really love the term wavicle, you do you, go with it. But for me, not so much. But whether we call it quanton or wavicle or something else, the main idea basically is outlined here. Okay, pick a quanton, any quanton. It could be a photon, an electron, a buckyball. Shoot it at a two-slit apparatus, and you're going to find an interference pattern emerge. So the question is why? And in our normal logic, there's kind of four possibilities. And these possibilities are kind of an exhaustive list. Either the quanton goes through slit 1, or it goes through slit 2, or it goes through both, or it goes through neither. Okay? Well, we know that it doesn't just go through slit 1 because we can do the experiment and see that we can look and we see that we find quantons in slit 2 also. Similarly, it can't only go through slit 2 for the same reason. The quanton is never measured at both slits simultaneously, nor do we ever measure half a quanton in one place and half a quanton in the other place. And item 4 doesn't seem sensible because if the quanton didn't go through either slit, you're not going to get any signal on the other side. So this exhaustive list of 4 options doesn't seem so exhaustive at the quantum level. And that's because quantons have a mode of being that none of the above with respect to these 4 options. The term that we will use is superposition. So a quanton is in a superposition of passing through slit 1 and slit 2. That is not the same as going through both slits. We are not saying that the quanton is going through both slits. What we effectively are saying is because we have not measured the path that the quanton takes, it does not have a defined position or a defined trajectory. It has a probability of taking one path or another, and we describe the experiment as the quanton as being in a superposition of going through slit A and slit B. And I just want to be really clear about what superposition does not mean. Okay, it does not mean that the quanton either went through one slit or the other, but we just don't know which. We're saying something different. We're saying that there is no path, there is no trajectory for the quanton. It's not knowable. It's not that we don't know it, but we could have. It's that it is not knowable because it was undefined. The quanton simply does not have a path. The quanton simply does not have a trajectory, so we cannot say that it went through one slit or the other. And this is hard, right? We have it's perfectly reasonable to have a mental model of a particle going from point A to point B along some path. And that just simply is not how things work in the quantum world, as far as we know. Prior to measuring a position of a particle, the particle does not have a defined position. And if it does not have a defined position, it does not have a defined position as a function of time, which is what a trajectory is. So as hard as it is to grasp and as weird as it sounds when I say it, this is the current state of our understanding of quantum mechanics. That particles do not have defined trajectories unless measured. They do not have defined positions, rather, unless measured. And so an unmeasured particle going through 2 slits does not go through either one slit or the other. It is in a superposition of going through both slits. For the rest of our time talking about quantum, we're going to make use of a related but different experiment that allows us to get at this idea of superposition in much, much, much more detail. So we have quite a wonderful road ahead of us. We get to talk about the nature of nature and what it means to have a quantum existence. And we get to think about what it really means for the property of a particle to simply not have a defined value until measurement. So hang on, folks. This is where we're going in the coming weeks. And in the next couple days, we're going to experiment with a hypothetical property of an electron called color and hardness. Well, two properties, one called color and one called hardness, as a way to build up some intuition for how quantum works. And then we'll transition to using actual particles, specifically silver atoms, and studying those particles and how they behave in specific experiments. So our quantum journey has begun. Hold on tight. It's going to be a fun ride. Take care, be well, and I'll see you next time.